Good morning, everyone. So the first talk of today is by Jason Lee from Princeton University on foundations of deep learning, stochastic mean descent, overparametrization, and generalization.
All right. Hi, everyone. Yeah, so of course, obviously, deep learning is super successful, blah, blah, blah. It solved a lot of stuff. It's successful in a lot of things. Some people have even gone as far as claiming it's the new electricity. Of course, when we have electricity, we should look. There's a field called electrical engineering that studies it, and I guess that's kind of the purpose of us being here this summer. So deep learning is not quite a science yet. It's fairly crazy that things, regardless of whether these things work, people will try crazy things like these cyclic learning rates. Learning rate tuning schemes are pretty crazy. They're fragile, even things like changing seeds. And it's sort of like we're trying to build a working system via trial and error instead of understanding something like civil engineering. And then, so sort of, Ben, our deep learner, has built this thing. But he didn't take his structural engineering class, so that's what happened. So this talk is trying to understand deep learning. So motivated, of course, by this well-known paper. I added an optimization at the end. I think they left out something pretty important there. OK, so understanding deep learning, so there's obviously two aspects. Our goal is to minimize test error. We want to do, say, multi-class classification. As usual, you can think of it as two components, an optimization error and a generalization error, something controlled by the algorithm and something simply statistical. So there's, of course, this problem is challenging in both aspects. The optimization's non-convex, non-smooth. The global landscape, probably nothing is very good about it. Lots of local minima. And just in general, it's difficult to reason about. The only thing we can see are really gradients and Hessians and so forth, local information, and you want to draw global conclusions. On the statistical side, similarly bad. There's more parameters than samples. The generalization error literally depends on everything: your algorithm, your learning rate schedule, your architecture, initialization scheme, algorithm parameters such as momentum, so forth. OK, so how to deal with optimization? Luckily, this is probably where it's most well understood. Is simply people have realized that you can always change the model. That if one model is difficult to fit, we don't have to believe any model is correct or anything like that. You just fit a bigger model. And bigger models are easier for SGD to fit, which is somewhat of an empirical fact by now. So you can have this model with many bad local minima, do something, and then SGD works. So overparametrization. OK, here's an experiment showing this. This experiment is essentially replicated from this paper of Livni, Shamir, and Shalev-Schwartz. So on the left-hand side, the data comes from a teacher network that's fairly small, compact. It has 50 neurons. On the learner side, the network has double the number of neurons. It has 100 neurons, but still the data comes from a network with only 50 neurons. So if you try to run SGD on the well-specified architecture, which is very sensible, assuming you sat through a statistics class, if the model comes from the family, you want to be well-specified, MLE's asymptotically efficient, whatever. But at the end of the day, SGD fails, so statistical efficiency doesn't matter, right? If you can't get training error low, why do you care about statistical efficiency? Because you cannot find the MLE. You run SGD 5 times, it gives 5 different answers, none of which are the global minima. I could have done this 5,000 times. I don't think you would have found the global minima. OK. Now, in stark contrast, simply the data comes from the same source. And I simply slightly change the architecture. The only thing is doubling the number of neurons. And I run SGD, again, 5 times. And every single time, it hits loss value 0. Okay. And this is also test error. This is SGD on fresh draws of data. This is not training error. Okay. So SGD is finding the global minima of the population loss empirically. So seemingly overparametrization does, in fact, make optimization easier. And in this case, even made, because it's test error, you could have even extracted some statistical statement here. OK, so recently in a series of papers by myself, Yuanzi also briefly talked about this yesterday. Chen has also worked on this. I'm summarizing all of these results because they're all kind of similar enough that I don't want to spend time distinguishing. They basically say if you have very wide networks and you initialize randomly with appropriate variances that are not crazy, gradient descent converges to an epsilon global minimizer. As long as the loss is convex, your learning rate is small. Roughly speaking, it works for any model. Okay. So when you're sufficiently overparameterized, you get an epsilon approximate global minimizer of the training loss. Let me sketch a proof of why this could be true. Of course, when you're overparameterized, looking at the parameters is not a great idea. They're not identifiable. There's permutations and all sorts of other invariances that come out that the parameters don't really respect. It's a better idea to look at how the prediction changes. So if you compute the change in the loss, you'll find that it's related to the outer product of a certain Jacobian matrix or the Gram matrix. As long as this Gram matrix is strictly positive definite, you get a contraction. Then if I could ensure that this thing stayed positive definite, then you converge to a global minimizer. So why does this stay? First thing is to establish that it started positive definite. That's pretty clear. Random matrices are positive definite, so this is sort of just a concentration and perturbation analysis to show that initialization, the Gram matrix state is positive definite. And then simply when you're very overparameterized, M is the width of the networks, then it stays positive definite. There's always hiding a bunch of stuff. It's whatever, it's something, and then you need M big enough to make this smaller than lambda 0. Okay, so overparameterization, essentially what it does is it's forcing, in this initialization scheme, it's forcing the Gram matrix to stay very stable, close to its initialization, and thus stay well conditioned. And finally, you get the grade. From this, you can extract statements of this type. For square loss, you can say it exactly converges to global minima at a log 1 over epsilon rate. If this was, say, logistic loss, you could say that it converges to an epsilon global minimizer, where epsilon is determined by the width. If you wanted it smaller, you would need wider, because logistic loss is not globally strongly convex, it's only locally. But regardless, for wide enough networks, as long as your loss is any convex function, you can get a statement like this. Okay. So so here's a simpler way to interpret these statements if you don't want to read 15 pages of calculating algebra. One way to interpret these statements is a statement about the local geometry of the loss function. You take your random initialization, draw a ball around it of some norm C. For some appropriate C that depends on the width you set. Every critical point in B is a global minimizer. And there's at least one global minimizer here, and GD sort of stays in this set. So it's a statement about local geometry. It's saying that locally, things essentially look convex. As long as you find a critical point in this local set, it will be a global minimizer. And in fact, you do stay in this set. So roughly, the global geometry of deep networks it's probably pretty bad. I think there's definitely, it should have exponentially many bad local minima with even high values of train loss. However, locally, there is a global minima. Locally, there exists global minima. And you can find a region in which there are global minima but no local minima. No local minima of higher loss than 0. Yeah.
Do we know that there are local minima for those networks?
Yeah.
How do we know that?
One way is you take an underparameterized network and start introducing neurons, and then set them to be to sort of cancel each other. Configure the ways you add them in a way that cannot help.
That's true, but it's very unstable, right?
But it's still a local minima. At least I can make it a higher order saddle, I'm certain. But I'm not saying you'll find them. Yeah. I'm saying there are ones. And certainly not near random initialization.
For very special architecture.
No, I think I can always do this. I take your architecture and just make a tiny one if you believe there's one in a very small architecture, I start augmenting neurons in some useless way. So it'll look like a standard architecture, but maybe the parameters will be in a weird configuration, I think. At least I can make a saddle, I think, high order saddle, I think. Okay, so global geometry, probably not very good. Local geometry, very good. There is a global minima and gradient descent converges to it. So we're kind of happy. And then you think about it a little bit more, and then some papers start coming out, and then you realize, of course, locally it's very good. Locally, you can write down any function. So f theta is my neural network function. It's essentially equal to some f0. It's not important. Think of f0 as 0, or very close to 0, some order 1 quantity, a gradient term, and a second order term. So of course, since I'm local, the second order term should be thought of as smaller than the linear term. So we kind of just throw it away, and that's what these papers are doing. And then, so what's happening here is that if you're able to change the predictions f of x by an order 1 quantity, while the Jacobian, the gradients, stay constant in a relative sense, then the second order term is essentially vanishing. The second order term is how fast this changes. So if I can move f of x by order 1, which is all I need to move it, because I need to move it to match y, while this stays constant, then I'm done. I've constructed a global minimizer that is very close to my initialization, close in the sense that there's no potential negative curvature. And that's essentially what that proof was saying. It was saying this H of the H matrix, the gram matrix, is simply the outer products of these gradients, and it was not moving a lot under these initialization schemes and widths and so forth. Okay, so Shizat and Bach came up with a nice sufficient condition of when you should expect this, they call it this kernel regime to happen. Essentially, the sufficient condition is that think of y minus f0 as order 1. We initialize a network, so it outputs an order 1 quantity that's random. So this is like 1, because y is order 1. And they basically pointed out that if your Hessian divided by the square norm of the gradient is smaller than 1, then the second order term doesn't matter. And your gradient dynamics track very closely for some constant amount of time the dynamics of gradient descent on a kernel machine. Okay, this is very intuitive because it's essentially saying exactly that how much the Hessian changes is very small to the gradient, and the gradient, when the gradient is big, then you only need to move the parameters a little bit, and you move your predictions by a lot. So roughly, in all of the ways we initialize, the Hessian is something like going to 0 with the width, and the gradient is O of 1. And so we have this sort of linear behavior in some region around the initialization. Okay, so any questions here before I move on to something else?
So, Jason, how do you think about a result like this? Are you saying that the final state is a perturbative approximation of the initial, and that this linear approximation is good? Is this sort of an idealized model motivated by a deep network? I mean, how do you think about this? Given this, you could ask all sorts of other questions. You could ask, you know, is a linearized analysis appropriate? And does this eigenvalue spectra change? So, how are you thinking about a result like this?
So this result I would think as if this sufficient condition holds, and you use a very small learning rate, then the gradient on f theta sub t, and you can construct a new function that is linear, call it f bar theta t. These are very close for a constant amount of time. So the gradient dynamics track those of a gradient dynamics on a linear model for some amount of time.
Right, but that's like a statement of the result.
Yes.
How does that relate to the motivating slide you had up front? It was a set of empirical results. The Jean was, a set of empirical results on state-of-the-art models.
This.
No, 5 slides. The first or second slide. One of these sort of things.
No, this is not state-of-the-art models.
There was the ICLR thing, Jean's, the Google thing from a few years ago.
No.
That was on a state-of-the-art something out there, right? And they did a D. This
paper was about. This was about generalization. I'm only talking about optimization right now. This paper is about generalization. This statement has nothing to do with these. I mean, you can extract a statement about statistical error here, but it's not a strong statement. This is really an optimization thing, I would say. It's saying that.
I mean, that's what I'm asking. What, in your mind, what does this say about a state-of-the-art motivation like that? Because would you be able? I mean, you could ask whether the initial configuration, the final configuration, are close like this.
They're not close. They're not close like this.
So I mean, what in your mind, what guidance does this sort of theory provide for a situation like that?
I think it tells you that you can get training error small very quickly initially in the first few steps.
So this is someone on the line for my class. So it seems that one could come up with empirical protocols to somehow see how relevant this is to what's going on in practical models. So you said a word about they're not close. Does that mean that we run experiments and we know that this does not really capture what's going on in standard models?
Yes, there's empirical papers, not by me, but yes.
Empirical papers that say that this is not.
Yes.
And is there any evidence that indicates otherwise, or is it a consensus?
I mean, it depends on like your parameter settings. If you set the learning rate small, it agrees well.
I'm talking about practical, baseline, off the shelf, more or less. 'Cause
if you set the learning rate big, then no, it disagrees. If you set it small, it agrees.
yeah, but there are certain values that we usually use in practice, so.
And the ones that get good test error disagree.
Okay.
So this is actually a pretty simple question, I hope, but how should we think about Hessians for models that don't actually have Hessians?
You should think about it as, okay, one quantitative way to think about it is the change of the activation pattern, which is the second derivative. Sigma prime is the activation pattern, and sigma prime prime is how much those change in some measure. Yeah.
And so the hashing is in order of 1 over root.
Yeah.
The distance moves in this order rather than
Sorry, say that again?
the distance between the hashing at theta and theta 0. That is in order of 1 over root hashing.
No, the Hessian is of order 1 over root.
Itself.
The Hessian itself. The Hessian, you don't care about the Hessian's movement. What you are worried about is the gradient moving a lot, because that means your feature scheme is moving a lot. You want to ensure the feature scheme does not move. So you need to bound the size of the movement of the feature scheme, which is the Hessian, relative to the size of the gradient, because the gradient multiplied by your movement is your change in f. That's why it's a relative measure. Yeah.
So which norm you are measuring the Hessian potential matters, right? Because the size of the Hessian.
Everything in Shizat and Bach is the only parameter moving is m. So then the norm doesn't matter.
But the size of the parameter depends on m.
Oh, sorry, it should be L2 and spectral. Okay. Yeah. But everything in that paper pretends the only thing changing is m. Yeah.
Sure. But I mean, just even the size also depends
Yeah,
on
yeah, yeah. It's spectral.
What's the dependence on like depth here?
If you're careful, it's polynomial. This paper doesn't talk about it. I'm not sure they talk about it. Okay, so somewhat this at least tells us that at least locally optimization is not a big deal. So perhaps you can believe that if your learning rate initially is not very big, you can get your optimization error kind of small. If you try to use this kind of method to get an analysis of generalization error, unsurprisingly, since your feature scheme is not changing, what you'll find is simply it has the same prediction exactly as that of a kernel method. The kernel is called the neural tangent kernel, and your generalization bound will look exactly like ridge regression. It'll be something like lab y transpose kernel inverse y over n, whole thing under square root. So that's some generalization bound you can extract from this style of analysis. I don't think it's very tight. In fact, I'll talk about later. It's not tight. I remember. Okay. Okay. So let's look a little bit more at generalization error, what's happening. A very standard bound in generalization error is some complexity over n. For example, in kernel methods, it would be y transpose k inverse y. That's sort of the RKHS norm in ridge regression. It could be VC dimension. VC dimension is roughly number of parameters times the depth in feed-forward networks. But regardless, they're all kind of big. They're bigger than sample size, which is exactly what the iClair paper was pointing out. It was pointing out essentially that the number of parameters is roughly 30 times the number of samples in many models. And of course, so this slide is stolen from Nati, or I think from Tenyu actually, who stole it from Nati, and I copied it from Tenyu. So we've all seen this many times, I'm sure by now. So what they did in their iClair paper is the number, so the black line is the training curve, and if you took statistical learning, you would kind of expect the red line kind of goes up. It doesn't, it goes down. And overparametrization does not seem to hurt generalization in this case. In fact, in this one example, it kind of helps a little. You can improve your generalization even after interpolation. And there's even more evidence that number of parameters is not hurting. If you plot ImageNet top 1 error over time, then you see that in fact, for these very, very big networks, the top 1 error is quite small. It means decreasing here. I mean, this is cherry-picked from this paper, but there's clearly networks with 600 million parameters, and it has test error very low. So throwing in parameters in a non-stupid way will not hurt your generalization empirically. Okay, so what's going on here? Let's turn to margin theory and see what it tells us. So this margin theory is very classical. It basically says that if you're very far from the decision boundary, you should be very good. Why is that? Bartlett and Mendelssohn told us this almost 20 years ago now. Basically, your generalization gap is upper bounded by some complexity measure divided by the margin. So if you can ensure some sort of Rademacher complexity that's sort of size-free, independent of the width, then you can get good generalization error. So here are some papers that talk about how to upper bound the numerator here. I'm only going to talk about how to lower bound the denominator. Okay, so how do you get solutions with good margin? Let's look at the simplest loss function with the simplest regularization scheme. Is you have logistic loss with some norm regularizer. For example, weight decay, L2 norm. You would kind of hope, so this is the global max margin. This is the best you can do if you search over all models in your parametric family, and you kept the one with largest margin, gamma star. So you would hope you can get gamma star. And in fact, if you do a very good job of minimizing this regularized functional for small lambda, then you do get gamma star. So in other words, a weak L2 regularization leads to, assuming optimization works, weak L2 regularization will get you very high margin, the best possible margin in the family. Okay, this proof is simple, unlike a lot of Yuanzi's proofs, I think. This is genuinely simple. Okay, the proof is essentially you write down the logistic loss, realize that logistic loss, when this argument is very small, can be approximated by Taylor's theorem, and that gets you an exponential. Exponential of a lot of terms added together, you only need to keep the smallest one because the rest are exponentially smaller. Okay, so this line is Taylor's theorem, and then this one says if you add a bunch of like e to the minus 10 plus e to the minus 100, you only need to care about e to the minus 10. Okay, so only the smallest of these terms matter. That's why there's a min here. And then from this, you can kind of read off the results. If you let lambda very small, it's saying, let me use as much norm as possible, but among those, I need to make the worst case margin good. So among solutions of the same norm, we prefer the largest margin. Okay, so how does overparametrization improve the margin? This is completely obvious. If I have a network and if I have a subnetwork of this network, the margin can only improve. So if you have a Rademacher bound that's independent of the explicit number of parameters, the margin is only improving. This denominator can only get bigger. Okay, so let's talk a little bit about how to optimize when you have a regularizer. The first thing to realize is that none of these results using NTK and locally convex or whatever can ever handle this. The regularizer induces a sort of tie breaking among the global minimizers, and the global minimizers are not equivalent. Like, you can have two global minimizers with unregularized train loss, and they will have drastically different regularization effects. So the regularization induces a tie breaking, and now you really do need to find like a global minimizer of this regularized objective. So how to do this? The answer is not fully satisfying, but we can say something. So take a very, 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 very wide network. Think of this as like wider than anything you've seen, exponential in D or exp D, whatever, infinite. Okay, then run gradient descent with a particular noise scheme. Then you converge a global minimizer in polynomial time, polynomial in the dimension, and in 1 over epsilon, something like poly D over epsilon 4 or something. Okay, so gradient descent on very, very, very overparameterized networks converges to global minimizers. So overparametrization does help even when you have regularization. The mechanism in which it helps is very different from this local convex intuition. The intuition here is that when you're very, very overparameterized, there's a descent direction in function space. But if you have a small width network, you might miss the function space. You might miss the direction of descent in the function space. That's essentially what Frank-Wolf algorithm would do. But computing a Frank-Wolf step is exponential time. So, but instead, if you had a ton of neurons and you add noise, then there might be an exponentially small fraction of your neurons that see this Frank-Wolf direction. But then ReLU is homogeneous, and then although it's exponentially small signal, it goes up exponentially too. And these things carefully balance, and at the end, you do get a polynomial time result.
Yeah. So because the network's very large, what's the relationship with the NTK regime here?
This, no more NTK.
Okay.
NTK is gone, yeah. You change anything, NTK is gone. It's very fragile.
And so I remember some of these results depend on lambda being extremely small. So I mean, is there no balance there?
You set lambda in whatever way. Let's say you want gamma minus 0.1, and you set lambda depending on that. But it's polynomial time to get within constant margin. Polynomial iterations, not polynomial time. One iteration is exponential time, because you have exponentially many parameters. Yeah. So polynomial iterations. I should not say time. Yeah. Or time in the PDE sense. Yeah.
And one other question. So in the generalization bound, you were talking about a size-free Rademacher bound.
Right.
Obtaining the margin with
Yes.
very light regularization of the
Yes.
parameter.
Yes.
Of course, a Rademacher bound might depend on, say, certain norms, which then have to be balanced against this resulting margin.
Yes, you should think of whatever norms as this norm. Like, let's concretely take the Golowicz one, which is just a Frobenius norm of everything. Then that would be weight decay. Does that make sense?
Yeah, sure.
Okay. All right. So, so you might ask, okay. So why add this regularizer? I can already get the global min of the logistic loss without this regularization term. What am I getting here? Is my sample complexity much better? And it turns out it is. Let's look at a very simple data set. On the first two coordinates, the data looks like this. It's like 2 XOR essentially. Then every other coordinate is just standard normal. So there's 2 coordinates that have signal, and that's the ones you want to pay attention to. The rest of the coordinates are completely uncorrelated with the label. So they're noise coordinates to kind of fool you. And they exactly do fool a kernel method. A kernel method is unable to localize onto the first 2 dimensions, so it has to look over all dimensions. And it pays sample complexity at least d squared to get some error less. If you want error less than some absolute constant, you need to pay at least d squared samples, because a kernel method to solve this problem needs to at least form pairwise degree 2 polynomials that has complexity d squared. However, for that sort of 2 XOR construction, there's a neural net with 4 neurons. And then the sample complexity of learning a neural net with 4 neurons is something like 4d over n, so d over n roughly. So there's a clear sample complexity separation. With Regularizer, you can learn with d samples. Without Regularizer, you need at least d square samples. Okay. So regularization, explicit regularization, or not you look like.
I mean, without regularization, if you're not escaping the tangent kernel.
Yes, yes, yes.
But you might, I mean, you could, it's not, you could escape it also without regularization.
But we don't, yeah, it's not clear. Yeah, yeah. It might take exponential time.
I mean, we don't know.
We don't know. Yeah.
I mean,
No, we know it takes exponential time.
well, it depends how, I mean,
Depends on how you scale things, but I can scale it so it takes you exponential. But then you could increase your learning rate. But anyway, let's not get into that.
I mean, it's not saying that you have to have regularization. I mean, it's just you're comparing your regularization to the tangent kernel analysis in a specific setting. I mean, it's
Yeah, I guess I should be more precise. To be more precise, this one is better than the NTK one. Let's put it that way. So then it covers the unregularized and the regularized case. Okay. So do you need regularization? It turns out you can do pretty well if you look at these numbers without regularization. So like the gain here is not from regularizing. You gain 5%, but if you just change the architecture, you can gain around 10%. So SGD without regularization does already have very good generalization. Perhaps it's not state of art, but it's certainly, the bulk is not from these regularization methods. Okay, so let's turn to a simple example of logistic regression. So even if you have separable logistic regression, the problem is convex, but not strongly or strictly convex. So there's many, many global minimizers, and you may be wondering which one does it converge to. This is exactly what Sodry, Hoffer, and Strebro asked a year or two ago. And they showed that this converges to the SVM solution in a very precise sense. If you run gradient descent for a long, long, long time, then you normalize because the norm blows up. You get exactly the L2 SVM solution after doing some normalization. This is quite amazing if you haven't seen it before. There's all these directions. Why the heck should gradient descent get the one of minimum L2 norm? That maximizes the L2 margin, right? I mean, this seems, maybe it should depend on learning rate, how you initialize. It could depend on anything. And this result is quite stable. Any learning rate that's stable, it converges to the L2 SVM solution. Okay. So then, then you might be thinking, what is special about gradient descent? Let me write down gradient descent in a very suggestive way. I just write it down, so it's trying to maximize the correlation in L, yeah.
But it depends on the initialization.
No. No.
No, if you initialize in the orthogonal direction to your data, it doesn't matter.
Because the logistic loss gradient is never 0. So it's impossible to have a 0 vanishing gradient, even if you initialize orthogonal. This is in contrast to least squares, I think, which is what you're thinking. Yes. Okay. What was I saying? Yes, this norm. Okay. The important thing is that you write gradient descent in this suggestive way. So what it's saying is that gradient descent is trying to maximally decrease the loss value of the function while paying infinitely small amount of L2 norm. The key thing is it's trying to use the least amount of L2 norm to achieve this goal. So now you might ask, why don't I change a norm? And this gives you a family of steepest descent algorithms. And in fact, you can prove that for this entire family of steepest descent algorithms, you converge to the SVM given in that norm. Okay, so for example, L1 norm, this is exactly a form of boosting. Matus proved this a long, long time ago in his PhD, that in fact does maximize the L1 margin. The same proof works for all norms. Okay, so some examples, coordinate descent, which is steepest descent with respect to L1 norm. You're going to maximize L1 margin. It's not quite add a boost. It's add a boost with some dampened step size. So add a boost with a dampened step size that maximizes L1 margin. Add a boost itself does not. Signed gradient method, commonly used now to save on communication. This gets you some L infinity bias, and of course gradient descent is steepest descent with respect to L2. Okay, so that's great. We understand logistic regression very well. That's sort of always the starting point. So now the question is, what does it do on deep networks? If you're very, very, very optimistic, you may hope that it solves max margin, even if you do no regularization, because then you would have some generalization bound that only depends on this up here, and that seems good, because now you can get the optimal margin. Of course, notice that this is an SVM problem, but it's a non-convex SVM problem now. This SVM problem, unlike the linear case, has many, many stationary points. It has first-order stationary points, second-order stationary points, and a global max. So of course, you cannot prove that it converges to the global maximizer. What you're able to prove is that it converges to a first-order optimal point of the following SVM. This is some nonlinear program. It has first-order KKT conditions. And assuming the only assumption here is homogeneity, then if you do gradient descent on exponential loss, logistic loss, you get a first-order optimal point, first-order stationary point of this. Good. Okay, so you wanted to prove it gets max margin. That's probably not possible because you're running a local search algorithm. But at least you can characterize that whatever you converge to is very special in the sense that it's precisely a critical point of a fairly intuitive optimization problem. Okay, so I've talked about, I didn't really talk about the implicit regularization of NTK, but if you think about what kernel methods is, you can write down the sort of implicit bias of NTK, or the inductive bias of it, as sort of you're trying to find the thing that maximizes the margin, the worst case margin, but you stay infinitely close to your initialization. So this top one, theta hat k, is exactly what would happen if you did NTK on logistic loss and terminated after some amount of time, a very long time. You would approximately get maximum margin, but maximum with respect to a different sense, in the sense that you have to stay infinitely close to this ball. This previous result by us and Kaifeng Liu and Jian Li shows that actually you get a stationary point of this following program. In this program, you're letting the parameter move infinitely far from its initialization. So it's completely forgetting where it's initializing. It's running forever and ever, which you'll always do when you have logistic loss. And when you run forever and ever, you try to maximize the margin. Okay, these are, of course, two endpoints of an extreme case. On one of these, you're trying to stay infinitely close to your initialization. The other, you're moving infinitely far. So they're very different endpoints. Probably, in my opinion, what's interesting is probably when this is not quite zero, you're going slightly further than the linear regime, but you're clearly not going to this super asymptotic regime. You've deviated slightly from the NTK, and what is happening there, we don't really know. But I think that's probably likely to correspond to closer to practice than the other endpoint, because things like large learning rate, finite width, will cause you to sort of not stay infinitely close. Yeah. Okay, so the final thing I wanted to talk about is how does architecture matter? So I've told you kind of that gradient descent, asymptotically, the bias it gets you is an L2 regularization on all of the parameters. But that's sort of uninteresting. Why should you ever care about the parameters again? Parameters have no meaning in neural nets. The only thing that matters at the end is your function f. This is all you see at test time. The parameter is just a way to encode f. So what you should really ask is, how does this bias translate to over here? So what is the bias on the prediction function? And this is clearly where architecture matter. So for example, here, 1, 3, and 4, there was no regularization. The algorithm was just SGD. The only thing that changes is the architecture. Yet you get a huge improvement in the test error. Luckily, I don't know the answer for neural nets. But in linear networks, there's a very crisp answer. You can take a linear function, write it as a product of matrices. Then if you have L2 regularization on W's, which comes from gradient descent, it translates to a Schatten quasi-norm on theta, on the linear function. Okay, so regardless of the depth and the width, the prediction function class stays linear. You can write a linear map, a matrix, as a product, as one matrix, as a product of 5 matrices, is still a matrix. The function class never changes, but simply varying the parametrization combined with the algorithm changes the inductive bias here. And here you can characterize it in a very precise sense, that whatever gradient descent converges to is a stationary point of some problem with this Schatten quasi-norm. Okay. Similar phenomenon in convolutional networks, same thing. You can take a linear convolutional net and write it as a bunch of predictors. You also get a quasi-norm, except now it's sparsity instead of on the singular values. Okay, let me finish.
A quick question. When you say gradient descent, how do you choose a step size, or is it the flow?
No, it's steps. It's learning rate.
So what is the learning rate?
The learning rate is smaller than the local lectures.
It's the stability parameter.
It's the maximum learning rate.
Yeah. It's always changing, so yeah.
And this result doesn't depend on the choice of the learning rate.
Because this is again in the infinite, the norm goes to infinity region.
The function is infinitely flat asymptotically. So in fact, you could even grow the learning rate.
As long as the learning rate allows convergence.
Yeah. You need sufficient descent, in short. There's nothing funny about it. It's not small. Okay, so some random thoughts. Let me finish. So of course, we've seen now that by training neural nets that stay close to initialization, you can get kernel classes. So how to go beyond kernels, Yuanzi mentioned this yesterday. And of course, one thing missing here is how will distributional assumptions help? Most of these results have not used distributional assumptions in any meaningful way, I would say. I mean, there's a lot of results about learning single ReLUs, single convolutional filters that use Gaussian assumptions. Of course, you shouldn't believe in Gaussians. And and even then, you can see the Gaussian's not helping you that much. There were other ways to learn it, just maybe not quite gradient descent. So what are some reasonable distributional assumptions that can help us learn things? Because kernels don't really depend on the distribution, their optimization at least. So what happens right after the NTK regime? We figured out the endpoints in a sense. We figured out what happens locally. We've figured out what happens if you move infinitely far. But the whole middle, I don't know. It's kind of interesting. And architecture, design, and inductive bias. So people come out with new architectures every week. And how does this change the inductive bias of SGD? If I do SGD on ResNet versus AmoebaNet blah, then what is changing here? Let's say I just use SGD on both. But the functions I learn are different. How are they different? And why does AmoebaNet whatever generalize better? Thank you. That's all.
What are situations in which one would prefer GD over SGD based on all the results you have?
Nothing. GD is just easier to analyze. Most of the results hold for SGD. Yeah.
Implicit regularization results, did you consider multiple? That was for single output.
No, that's a matrix. This one's a matrix.
This one is a matrix?
Yep.
Okay, and what exactly is the result?
The result?
The linear convolutional net, that's for single output?
Yeah. This one's a matrix.
So what is exactly the result?
You minimize. There's two results. One is you minimize cross entropy with explicit weight decay. You get the quasi-norm. Second one is you minimize cross entropy with GD.
You minimize cross entropy with explicit regularization, then you get the minimal Schatten quasi-norm solution that reaches close to zero loss? Or
Yes.
Okay.
No, there's no optimization. These are statements about global minimum. Okay, the first statement is a statement about global minimum.
Yeah.
Okay. The second statement is invoking this following theorem. It says that you converge to a first order optimal point of a problem, an SVM, where this is the Schatten quasi-norm. So the inductive bias of having deep depth in a linear network using logistic loss is getting closer to Isaac rank.
And this result is regardless of that's a result on the global minimum, no gradient?
No, this is about first order. So, okay, so gradient descent.
Algorithm is not relevant?
The algorithm is involved here. It's about gradient descent. You run gradient descent, something happens, and what happens is it converges to a first order stationary point of a problem where this is a Schatten norm. It may not be the global minimum because it's non-convex, but it's a stationary point of the Schatten norm problem.
Okay, I guess that's